All right, welcome to lesson 5 of unit 2. This is all about inverse relations. So before we dive into our lesson, we've got a couple questions here, just looking at solving for x and looking at the idea of moving equations around. So we don't have a value for y, so you're literally just trying to isolate x so that you end up with a final statement of x equals something. Okay, so if you want to pause the video and try your hand, these are skills that you should have developed in your grade 11 and earlier pre-cal courses and other general math courses before that. So give it a pause, give them a shot, and then check your answers when you're ready. Okay, so how'd you do? Just a quick reminder that we always kind of work from the outside in and do opposite operations to try and isolate x. So that's why we've added 4 to both sides before we divided by 3, kind of stripping off the outer layers to get to the term, and then breaking down the term from there. So the other thing that we need to kind of review is the idea of a function. So a function is a rule that assigns to each element in the domain exactly one value in the range. So I'm never going to have one number in my domain or one x value that could equal more than one thing. The second that this happens, or the second that I get something like this, where x equals 2, y could equal 4 or 5, this is no longer a function. So most of the equations we've been working with in our history have been functions, just kind of as a rule, but we do have some that aren't. And how we always check is by doing a vertical line test. So basically what we do is we take a line. So we take a line and, we try to drag it. So imagine a vertical line. This is what the vertical line test is. And at any point, if it crosses my graph more than once, that means that there's more than one output for that input, and it doesn't pass the vertical line test, so it's not a function. So this first function absolutely is a function. The second graph, though, is not a function because, with the exception of at the very ends, every time I draw a vertical line, and imagine that these are all straight up and down, I'm hitting my circle at more than one point, which means the second I get a hit here and a hit here for the same x value, it is not a function. So when we talk about reflecting graphs, and specifically inverse functions, we're talking about reflecting in the line y equals x. So this in itself is the definition of what an inverse is. So for all my French students, unfortunately, you use that word differently. You would have talked about inverse in the sense of fractions when I'm dividing. So like you would have had like 2/3 divided by 4/5. And you would have said, oh, when you take the inverse, and all of a sudden it's 2/3, excuse my French accent. You can clearly tell I'm an Anglophone. You would multiply like that. That is not what inverse means in English. Inverse means what we're doing today. So just note that we've got a little bit of language kind of confusion there. So you've been warned. So for a function y equals f of x, the graph of x equals f of y is the image of the graph reflected in the line y equals x. So that sounds super wordy, super mathy. We'll get into what that looks like in our examples. So the key idea here is that y equals f of x and x equals f of y are inverses of each other. So basically we're just switching it out and doing what we did in these examples here, isolating x instead, putting kind of it on the other side of the equal sign. So here is my favorite part of this explanation. the mapping notation, if we have xy as our coordinate point in y equals f of x, then our inverse function, we just literally switch x and y. They trade places. So what was now once your y value becomes your x value, and what was once your x value becomes your y value. When the inverse is also a function, we use this notation to the power of -1 to denote the function f inverse of x. Okay, so we'll be exploring what all of this means. And we start with that visual representation. So finding an inverse given the graph. So when we're using graphs, it's really important that we note that this is a reflection over, or in, you might hear that language, in the line y equals x. That's this line here. Okay, so just like when we were reflecting over our x-axis, any points on the x-axis were invariant. The same thing is going to happen here. So I'm going to have invariant points here and here. Everything else reflects across the line. So I'm going to erase those arrows just because they're going to make my life a little bit more difficult when I try and actually draw this graph. But what happens then is that I try and preserve that general shape. But flip it onto the other side. If I had values, I would use specific points, but since I don't, I'm just going to try and match the shape. So I would say that this is my f inverse of x. So again, that's the notation. And I know this is an inverse because, again, I can do my vertical line test and I never cross my graph more than once. Over here on the second example, we do not have any invariant points because we don't have any points that land on our y equals x line. But we do have a coordinate point, and this is originally going to be -2 and 0. So when we want our inverse function, it's going to switch these two around because remembering that xy becomes yx. Now all of a sudden my coordinate point is going to be 0 and -2. So 0 and -2. My x values become positive or more negative, and my y values become positive. So my y values should become negative and my x values should become positive, which means all of a sudden I'm drawing my graph like this. So that looks pretty weird, but that is in fact the trend. So we followed the rules of what we were seeing, and we used a point, a critical point, and our mapping notation to help us out there. And don't forget to label your graphs. So this graph will be nice because it gives us a few more examples. So I'm going to identify, first of all, I'm going to draw in that y equals x line. So again, that should be where my x and y values are equal. So kind of drawing through all these points here. -1, -1, -2, -2, -3, -3, etc. Okay, so that's my y equals x. That's what I'm reflecting over. If you don't like thinking about it as a reflection and you like the mapping notation version better, you're more than welcome to do that. Sorry, I'm a little sniffly. Okay, I'm next going to identify my invariant point, because I do have one. Yay! Okay, and then I'm also going to identify some other critical points that might help me out. So I've got this one here, that one there, I guess. These aren't lovely points to work with, but they'll do. Okay, so in my original function, I've got values of -7 and 1. got negative 2.5-ish and 6.5-ish. And then I've got positive 2.5-ish and negative 1 and 6. Negative 1 still. Okay, so when I go to do my inverse function, again, I'm just going to switch these all around. So using my mapping notation, my points are now going to be 1 and negative 7, 6.5 and negative 2.5, negative 1 and 2.5, negative 1 and 6. So again, the signs of the values don't change. The negative moves with my 7. It's literally you take the whole point coordinate and flip it. So when I go to graph this, I go 1 and negative 7, 6.5 and negative 2.5-ish, negative 1 and 2.5. Remembering my invariant point is still exactly that, so I can put that in there as well, and negative 1 and positive 6. And again, this gives me some help in terms of being able to sketch out my graph. And here, oops, there we go. And just like the ends on this original graph, I am now going to extend mine and put arrows on it as well, because everything about that graph is preserved, except for the fact that it's moved around. So that's my inverse. Now, question B is asking, is the inverse a function? So I take my vertical line, and from the very beginning, with the exception of right here, I'm just gonna, right here, great, I only hit 1 point, but the second I get over here, I'm hitting 2. Hitting at this point, hitting here, and so all of a sudden, I am no longer dealing with a function. So no, this is not a function, because it doesn't pass the vertical line test. And the more mathematical argument would be for more than one value in the domain, there exists greater than one output or value in the range. And that's going to be our mathy lingo. This upside down, backwards, capital E, means there exists. Okay, so just as some FYI. So this is a more mathy language. Does not pass the vertical line test would be a sufficient argument. State the domain and range of the function and its inverse. So we can't call the inverse a function because it doesn't pass the vertical line test. That's why I didn't use that f to the power of negative 1 notation. So for my function, f of x, my domain is from negative infinity to positive infinity. My range is negative infinity because it extends downward forever, all the way up to a maximum of about 6.5. I'm going to define it as touching there. Okay, my inverse if I look at it, my domain is kind of restricted. It goes to negative infinity here, but it maxes out at 6.5. As for my range, well, it extends to negative, it extends to positive, so I would say that the range is negative infinity to positive infinity. And you'll notice that they straight up flip, whereas we didn't see that in any of our other transformations. So again, that's what this is noting here. The domain and range just trade when we do the inverse functions. Example 3 looks at a different way of approaching this, and it specifically looks at how do we manipulate an equation so that we can get the equation of our inverse, whether it's a function or not. So that's what we're going to do next. Okay, so what does that look like doing this algebraically? Well, just like in our mapping notation, how we switch x and y, that's exactly what we're going to do. So our first step is rewriting the equation as x equals negative y squared plus 4. Now, it would be lovely if we could leave it like this, but that is not mathematics convention. We always like y always represents our output or our range, and we always like to have it out isolated on the left or on the right, just isolated in general. So we're going to have to reorganize this, and that's why we did what we did at the beginning of this lesson. So we're going to move this 4 first. So x minus 4 equals negative y squared. We're going to move that negative out of the way. So it'll be negative x plus 4 equals y squared. And the result then becomes the positive or negative square root of negative x plus 4 equals y. And so that would be our inverse. So when we go to graph this, I'll use black for my initial function. So that's negative x squared plus 4. So parabola, vertex at 0 and 4, opening downward, no stretch or compression. It's going to look like this. Still not great. Maybe if I put it this way, that's better-ish. Okay. So that's my original function. My inverse would be if I switch all these values, so 0 and 4 becomes 4 and 0, negative 2 and positive 2 is my vertices. Points over here, and so all of a sudden, apparently it doesn't make it any easier to draw horizontally. In fact, I feel like it might be harder because I'm just not as practiced in this, and you will possibly find the same thing. Okay. And there we go. And again, we want that parabola to look pretty curved at the bottom. Kind of like that. Still not super happy with that. You can play around with making this look nice and curved. I'm having some issues with my stylus. Okay, but that's my inverse versus my non-inverse. Is the inverse a function? Still absolutely no, because it doesn't pass the vertical line test. Okay. So let's do the same thing for this one. You can do it graphically, you can do it algebraically, whichever one you want. I prefer graphically when I can, but that's completely up to you. But if you want to pause the video and give it a shot on your own, I don't think that that would be a bad idea. Okay, so again, black is my initial function and blue is my inverse. So again, this is not a function, this inverse, because it wouldn't pass the vertical line test. So determine 2 ways to restrict the domain of y equals x plus 1 squared plus 3 so that the inverse is a function. Write the equation of the inverse each time. Use a graph to illustrate each way. So we've got a couple different options. We need to cut out basically half the parabola because that's where we're getting our repetition. So if we cut out the left side or the right side, starting at the vertex, that would be what would help us. So option 1 is to restrict domain to -1 to positive infinity. And what that would look like would be the original function versus the inverse function and now I can call it f to the power of -1x because it is actually a function. Conversely, I could also restrict my original domain from -infinity to -1. And what that allows me to do is basically do the other half of my parabola. And thus we're seeing this here. There we go. So those are our two different ones. And again, I would label this f of x and f -1 of x. Okay. So that would be how we can restrict it. So here we go. Determine algebraically whether the functions are inverses of each other. Okay, so to determine algebraically whether functions are inverses of each other, what we're going to do is we're actually going to take one and substitute it into the other one in place of x. And if we end up with the statement y equals x, then we know that it is an inverse. If at some point we don't end up with that, if we end up with any other values left anywhere in that equation, we know that it is not an inverse. Okay, so the key idea is substituting one equation in for x. So we can get, if we substitute into our first one, we've got 3, x minus 6 divided by 3 minus 6. Okay, well, when we have 3's multiplying and dividing, they're going to cancel out. So we've got x minus 6 minus 6. So y equals x minus 12. Because of this leftover number, that there's no way that it's canceling out with anything, there's nothing to cancel it out with, that means that it is not an inverse function of the function. Okay. If it had been plus 6, then absolutely it would have been. Okay. So again, we can check this here. With this restricted domain, we can rest assured that we're looking at only half of a parabola because our vertex is at x equals 0. So we check that part off and say, okay, we're good to go. And now we can test them out. So what do we get? Well, we go y equals, and again, I'm always going to plug this second one into this first one, just personal preference. You could easily go the other way as well. I prefer not working inside square roots, though. Just a bias I have. I find them less friendly than quadratics. Oh, the square kind of undoes the square root. If it helps to cross them out, that's usually what I do, just to help my brain remember. And that negative gets kind of distributed through the result. So I've got -3 plus x plus 3. Those 3's are going to go away because they're opposite signs. So we're ending up with y equals x. And so it is, these are inverses of each other. Let me just make sure I'm not missing any other examples I did on that previous lesson. Okay, so algebraically, that's how we check for inverses. We substitute one into the other. We can determine the inverse of a graph by choosing points and mapping notation. We can also think about it as a reflection over that y equals x line. And we could also figure out the algebraic equation for the inverse and graph that in instead. So whichever one makes the most sense to you, that's what you should do. But be able to feel comfortable answering all these different types of questions. And I'm going to put up some homework practice questions as well to help you out with this. So like usual, if you have any questions at all, please let me know, email me, put them in the sort of, which area is that called? The collaboration space. Okay, add a page there, or you can put it in your individual pages if you're not comfortable with everyone seeing the question you're asking. But either way, please make sure that you are asking questions if you get stuck, because that's the only way that I know that you're stuck, because you're not in front of me, unfortunately. But good luck, and we'll hear you in the next lesson.